So I can't help but notice you're empty-handed. Where's our merchandise?
Well, due to the round hull of the boat, the unbalanced weight of the bottle, the raised center capsule's center of gravity, there was a righting moment induced that could not be steadied.
So what you're saying is the boat tipped and you dropped it.
Yeah, pretty much.
That's what I get for sending an engineer.
Don't worry, sir. We can make alcohol in the bathtub.
If you wanted to drink dirty bath water, we would have stolen Budweiser.
Prohibition on. How are we supposed to get another brew unless we go down to the bottom of the lake and retrieve it?
Keep talking like that and you'll get an internship. We need someone to get down there, but how?
Oh, I know. We can use cement shoes. Isn't that usually how we put people at the bottom of the lake?
Yeah, but they don't usually make it back up.
You know, I've got it. We'll build a submersible and go down and retrieve it. We can't do it alone. You three, start assembling a team. So who's in?
David.
David who?
Electrical engineer extraordinaire.
Sure, but why is he right for the team?
You know how Alexander Graham Bell invented the telephone?
Yeah?
Well, David's the guy who connected the line. He knows a thing or two about getting wired.
Next, we have Willard. He's a student underneath Charles Babbage, the guy who created the difference machine, one of the first computers.
What's a computer?
That's exactly it. Nobody really knows what it is or how it works, but we thought having him on the team would help, especially when he's with his partner in crime, Nicholas.
This Nicholas character, is he any good? How would you rate his skills?
I think I would rate them a solid C++.
Next we have Adesh. He models for a living.
Like on catwalks?
No, like on SolidWorks.
That's deadly.
To ensure that doesn't happen, we have our safety liaison, Gabriel, with OSHA. He's the reason we stopped running on pool decks.
That's safe?
So last we have Momo, the guy that brings in the dough. When he was in engineering, he had more girlfriends than the entire department combined.
Wow, so how many did he have?
One.
Nice.
He also knows a thing or two about getting powerful people on our side.
Like who?
We call them our sponsors.
That'll keep our project's funds above water.
So what do you say?
Let's bring him in. We've assembled you all here today because you have a very particular set of skills. Skills you've acquired over a very short university career. If we can pool our skills together, we will look for the bottle, we will find the bottle, and we will drink from the bottle.
Yeah.
Nice.
Yeah, that's fine and all, but do we have a strategy for the robot navigating the water?
Well, luckily my associate laid out a path directly to the cargo.
Alright, go on.
Well, firstly, we have to place the robot in the opposite direction from where we want to go.
Opposite direction? Why would we want to do that?
If you're part of the mob, you always have to watch your back, buddy.
Okay, then what?
Next, we go through the gate with the bootlegger.
Why is there a bootlegger at the bottom of the lake?
He didn't watch his back.
Okay, is that all it does?
No, it'll also do a barrel roll as it goes through the gate.
That doesn't seem completely necessary.
Suddenly your share doesn't seem completely necessary.
Wait, I was supposed to get paid?
Okay, what's next?
Well, there's a G-Man buoy that we gotta ram into.
We should leave some markers in case we get lost.
Great idea. We can drop the markers in the sunken barrels.
Don't forget, the G-Man will be nearby with its weak spot exposed.
That's when we use the robot scat to shoot him dead.
Then what direction do we head?
My associate put a pinger on the bottle before we tipped it over.
Wow, that's suspiciously convenient. We could use a hydrophone to locate the pinger.
We want to grab the bottle that is in the middle of an octagon. Being inside the octagon keeps the sea bears away.
And surfacing in the octagon should be a good location to retrieve the precious cargo. Hey! And if we're concerned about the sea bears, let's just name our robot after a bear.
How does Arctos sound? The name's ancient Greek for bear.
I like it. All in favor? Wait on the boss, let's just go with it.
So what are we, some sort of autonomous robotic vehicle project?
That's too long, and you're terrible. You know what, let's just call ourselves ARVP.
Brilliant!
That sounds great.
Good job, boss.
Alright, get back to work, everyone.
A brand new robot was designed this year to accommodate 8 thrusters to provide 6 degrees of freedom, a rectangular hull, and all the needed subsystems. These major changes help improve on our previous robot's shortcomings by increasing spatial efficiency and rigidity while decreasing weight. All subassemblies have been redesigned this year to better adhere to competition scoring. Arctos is approximately 82 pounds and is designed to be slightly positively buoyant to minimize thruster effort to keep it below the surface. It is well balanced with the center of mass and center of buoyancy in line, meaning holding of any orientation can be done so easily.
The hull is encased in a minimalistic aluminum frame. This refined design uses 1-inch structural tubing and sturdy L-bars, connected with corrosion-resistant fasteners. Because of its functional design, drag forces are minimized. It remains light despite its 24 by 25 by 28 inch profile, which surrounds and protects Arctos' more delicate components. The hull is the core of our robot. The rectangular aluminum design makes it compact and space efficient. This way, we are able to include 5 batteries, the IMU, the NVIDIA Xavier processor, and all boards inside the hull for central access. We can access the hull's interior thanks to our front and top reinforced acrylic caps that have double O-ring seals to prevent leakage. Lastly, penetrators and subcons protrude from the back and sides to power and communicate with our external subsystems.
The electronics are secured inside the hull using 3D printed trays for rapid prototyping and design optimization. Electronic components are separated between the top and bottom trays by function and to augment better cable management.
The mechanical claw was one of our most exciting new additions to the robot this year. The claw was built with 3 degrees of freedom and is actuated using 4 waterproof servo motors. The arm consists of aluminum linkages connected with fasteners, giving the arm an excellent strength to weight ratio. The manipulator itself will be 3D printed using various materials to give it a strong grip while maintaining its structural integrity.
We redesigned our torpedo launchers this year, building on previous malfunctions and shortcomings. We transitioned from a design involving CO2 canisters and a pressurized chamber to a design involving spring-loaded torpedoes. This design eliminates the risk of leaks while reducing the weight of the torpedo's assembly considerably. Those G-men stand no chance.
The new marker dropper's assembly has a 3D printed body and is actuated using a waterproofed servo motor. The design is simple yet functional since each marker can be controlled individually.
To locate our merchandise underwater, we need a camera that faces downwards. This friction-fit assembly made of clear acrylic, PLA, and aluminum provides our fisheye camera with a secure 180-degree view.
Our main focus this year has been maintaining stability and porting the existing electronic systems to a new platform. Before that platform can go anywhere, it needs some form of propulsion. This is provided by 8 Blue Robotics T200s, powered by Zubac's brushless ESCs. Power is provided by 5 lithium polymer battery packs, one for every pair of motors and another for subsystem power. Each battery is routed through a custom battery monitoring board that monitors voltage and current, giving us real-time insight into power usage and preventing excessive draw on the batteries. With automatic input switching for the internal electronics, we are able to keep the core systems operational on the dock as we debug, pull data, and perform maintenance. This allows us to reduce wear on the batteries and continue to be functional for longer periods of time. An experimental feature this year is a battery leveling technology, which allows us to dynamically pull system power from different batteries, allowing for greater operation time and battery usage. System power is then further regulated into 3 rails, 12 volts, 7 volts, and 5 volts, by modular pluggable power connectors. And of course, in case the G-Man gets to us, we also integrate a magnetic kill switch into the hull, cutting power and allowing us to make a quick escape. And to detect if a run-in with the law left us worse for wear, there is an internal environment monitor, which monitors temperature, pressure, and leak sensors distributed along the hull. These measurements allow us to test for leaks before diving, before they become too serious in the pool. The torpedo actuator board was designed for self-defense, manipulation, and diagnostics. With a total of 12 servo channels, it gives us flexibility to run any servo-actuated system, such as our torpedoes or our actuator arm. As well, we have LED outputs that allow us to view the robot's state without a connection. In order to help us find our way, we also have an array of 4 passive hydrophones, coupled to our own sonar preprocessor board, which filters and amplifies the hydrophone signals and sends that data to the Jetson for processing to determine the pinger location. All of these systems then communicate over a single CAN bus, governed by the flexible UAV CAN protocol, giving us highly reliable and low latency communication and control backend, with Ethernet used for the high-speed data transfers.
The purpose of the software team is to enable Arctos to maneuver itself to a desired goal using the tools given to it by the electrical and mechanical teams. To do that, we have a 3-stage software pipeline. We perceive our environment, set a goal, and then act on that goal. Our sensor suite allows Arctos to measure depth, velocity, acceleration, and orientation with the assistance of a depth sensor, Doppler velocity log, and inertial measurement unit. Arctos uses neural networks YOLO-V3 and YOLACT to see its environment. These achieve rapid object detection and instant segmentation respectively. Our new Z stereo camera now allows us to measure distance and generates a mesh of 3D objects on the fly. For an estimate, we have a mapping system that combines sensor data to create a map of the competition area. This includes Arctos' position as well as the various props in the pool. We have a robust mission planner that accounts for task failures and unexpected events, ensuring the robot accomplishes tasks within the given time constraints. Even if the robot fails a task or cannot find an object, our mission planner ensures Arctos will keep on going. It is very easy to use and is able to create missions for any scenario. A positional goal from the mission planner is converted into a series of velocity goals over time. These velocity goals are then inputted into an LQR control system which controls the thrusters to reach velocity goals. Our LQR control system has reached a strong level of maturity. It uses a mathematical model of Arctos and a linearized dynamic model of the underwater system to reach velocity goals. This system allows for simultaneous control in every direction and is readily able to account for physical changes to Arctos, such as adding a camera or sensor.
Our most important tool is the simulator. It allows us to test outside of an actual pool in a realistic, simulated environment. We can simulate sensor data, test the accuracy of computer vision algorithms, measure how well our mapping system converges to a simulated environment, and use our mission planner to run practice missions. This year, we migrated from our older UW Sim simulator to Gazebo. This has been instrumental in testing Arctos' ability to interact with objects where collisions and manipulation are required. Gazebo also has a timescale acceleration factor, allowing the testing of long missions in very short periods of time. Working remotely has been a challenge. We've been forced to overhaul our documentation. The WikiTool Bookstack allows us to organize and create internal documents. Hosting Bookstack on our web server makes it easily accessible for all of our members. Since we can no longer participate in face-to-face outreach, our website has become our primary platform. Our previous website was 5 years old and difficult to maintain, so this year we have decided to overhaul it with the Oxygen Page Builder. Our new task management tool, Trello, allows us to subdivide large projects into small, bite-sized tasks that can be assigned to individual developers. This has increased our focus, productivity, and has allowed us to quantify the work we are doing. We can visualize how many task points and pull requests we accomplish per week in Google Data Studio. We use Docker and Travis CI to build our codebase and run a suite of tests every time a developer makes a code change. This ensures that our code builds and works when we release it to Arctos.
Well, boss, here you go. Here's the merchandise.
Well, we did it. Nothing more rewarding than a well-engineered solution to a relevant problem.
Boss, gentlemen, just letting you know, Prohibition has just ended, so we don't even have to go and get that bottle. We can just go and buy some more. I'll leave now.